These are resistors with color coding. The typical 4-band code here, sometimes you'll have 5 bands, but you've got the first 2 digits right there. It basically gives you what the resistance is to 2 significant figures, and plus an error bar. So those are the first 2 for significant figures, followed by a multiplier factor, which is going to be some power of 10, and then this is how accurate it is. The silver band here, which is the last one, tells you that plus or minus 10%. The color code, I'll just zip over here to the color code. And you notice down here, silver, 10%. We have a couple gold bands, and I think we might have a gray band somewhere. But most of the cheap ones that you get are going to be 10%. So as you read the code, we'll take the middle one because I can identify those colors a little bit better. You have sometimes it's hard to tell. I think that's a red right there, but not always easy to tell. All right, so that color right there to me looks brown. And brown corresponds to the number 1. Then you have green, which corresponds to the number 5. So that is 15 times orange, which corresponds to the number 3. So that's 15 times 10 to the 3rd power, plus or minus 10%. So this resistor here should be about 15,000 ohms. And so let's go find out. So this is the one that I'm guessing is going to be 15,000, assuming I've read those colors correctly. We have a multimeter here. So we have a multimeter and that one. So I'm going to clip this to this side over here. Ideally, I should be able to clip this to the post, but there's so much oxidation that's happened, and there's a layer there that adds extra resistance that it's usually easier to connect it to just the wire itself. Every time we clip it, we scrape a little bit of the oxidation off. Not ideal. Eventually, those are going to break, but until then, we're good to go. Probably should take a little bit of sandpaper or something to it, maybe a Dremel, carefully. I want to make sure that there's a secure connection. And I think so. It's not sliding easily. And we'll put this up. And we see what it comes out to. So notice, it is 15,000. And the K there is the thousand. So it's 15.11 thousand ohms, or 15,110 at the moment, 120 ohms. So it's definitely within 10% of this value right here. Matter of fact, it's within 1%. And so that's how you read the color coding. For this next exercise / lab, depends upon how I want to use it, I'm basically looking for all of them that have the orange band in the 3rd band. If I had a 5-band resistor, and we do have a couple of them floating around, I don't think I have any here, I think they're at school. But if I have 5 bands, then the 4th band would be the power, and the 5th band would be the tolerance. In other words, the plus or minus 10%, like the silver band is. And so I'm looking for 6 resistors, which all have the orange band, and then we will label them. And they have been labeled already because of, I think, some group who did this lab last summer. So actually, while we're here, the one that I have tested, so we'll just write it down. That's the one with the 2 on the bottom. So number 2 was 5120 ohms. This one is number 3, and I'm pretty sure that first color is, I think it's red, violet, orange. Orange is sort of coming off there. And so if that's the case, red is 2, violet is 7. So I think this is going to be about 27,000 ohms. And that was number 3. And is indeed 27,003. Can't seem to make up its mind. All right, so that's number 3. Number 6. Again, make the prediction beforehand. That looks like brown, black. So that would be 10,000, I would guess. That was number 6. So here's a 1. We got, looks like brown violet. So 1, 7, so it's about 17,000. It's got the 1 on the bottom. Oh, and this light, that's brown gray. So about 18. Need a 4. Here's 4 right there. And that looks green blue, and that's on the light I'm looking in. So that should be about 56,000. Then something with a 5 on the bottom. Now I don't necessarily, there's nothing special about these other than some student in the past has written on them. It definitely does not look like my handwriting. Well, at least some of it's way too neat. This one is yellow. I'm going to go violet. So this would be 47,000 if I'm looking at the color correctly. Also pointing out some of the issues with colors is that sometimes it's difficult to really tell what the color is. So I have my 6 resistors, and so now it's a matter of setting them up into a circuit. So let's go through the math for it. How do I want to set this up? Matter of fact, I'm going to come back for part 2 on that one. Here's the basic setup of the circuit, and so we'll just do this in order. So that's resistor 1, 2, 3, 4, 5, and 6. So theoretically, we can find the equivalent resistances of, we can find the equivalent resistance of A and B. They are in parallel because they have junction on both sides of them. And so those are the resistors in parallel. 1 over the resistance of A plus 1 over the resistance of B equals 1 over the resistance of this equivalent resistance AB. So 1 over 18,210 plus 1 over 15,120 equals 1 over the equivalent resistance. 18,210, 15,120 plus reciprocal. And so my resistance of AB, the equivalent resistance of AB is 8260.882. Now, do I need to take it out that far? It actually turns out yes, because I've done enough of these labs right here that if you round off too soon, that ultimately when you're making predictions for current, they come out horribly. But they don't come out if you take it out more decimal places than you think you possibly need. Matter of fact, let's take it out to 4 decimal places. I've basically taken this and I've turned that into 1 resistor right there. So we can now redraw this. So I have my AB here, C, D, F, E. And so I can now find ABC because they are in series, so we just add them up. And C is the 3rd resistor, so I add 27,300 to it. So 27,300 35560.8821. That's the equivalent resistance here. So now I can reduce it a little bit more. A, B, C. Then I have D here. E, F. These are in parallel right here because they have a common junction before and after. Now it doesn't look like a single point like junctions typically are, but remember these lines right here represent frictionless wires, wires without any resistance at all, superconducting wires in a sense. Because there's no resistance between these 2 points, there's no potential difference between the two, and therefore they're equipotential. And so that is a junction. So they are in parallel. So 1 over the resistance of ABC plus 1 over the resistance of D would be 1 over the resistance of the combination ABCD. So we have 1 over 35,560.8821 plus 1 over RD. D is the fourth resistor, so 56,300. It's going to be 1 over the equivalent resistance. And so again, pulling out the calculator, take the reciprocal, 56300, take the reciprocal, plus reciprocal. And so the resistance of this ABCD combination, so of all four of these resistors, or in the original sheet, all 4 of these resistors, the equivalent resistance is 21,794.6706, rounding off to 4 decimal places. And so now we've reduced this down to, so I have my power supply. Then I've got this junction up here with D in it. This is my A, B, C, D. And that's what it's reduced down to. Because remember, this ABCD combination right here basically happens before F and E. If I went through this path right here, I could go through E, or I could bypass this path completely and go through F. Well, I can bypass, go through F, or I can go, if I want to get to E, I have to go through that combination. So now ABCD and E are in series, and so my equivalent resistance among these is just the sum of the two. So that was 21,794.6706 plus E. And E was the fifth one. That's 46,800. 68594.6706. And so now we have come down to, I've got my power supply here, I have my resistor F, and then I have my resistor A, B, C, D, E. And F is the sixth one. This is 9560. And they are in parallel. So 1 over this plus 1 over 9560 is 1 over my total equivalent resistance. My total equivalent resistance of all of it, 8390.6060 ohms. One reason for going through that is that we can check that answer, but also it'll help us sort of work backwards as well. We can now find the current coming out of the power supply. So if I've got a total equivalent resistance of 8,390.6060 ohms, well, I can now find the current coming out of the power supply. This is some current I. I'm going to put I as a PS for the power supply. I know that the potential gain across here, I'm going to lose going across there. In other words, my potential drop is going to be equal to whatever my power supply is times IR. So my current coming across the power supply is just going to be whatever my voltage across the power supply is divided by that total equivalent resistance. And that is something we can actually check. So let's actually come up with a value. 13.77 volts, if we worked with that, the current coming out should be of 1.64112 milliamperes is what is going to be flowing out. Now we have to start working our way through trying to figure out what is the current flowing through each of the branches. So this is what's coming out of the power supply. So looking back at my original drawing, so we established that if the voltage here is 13.77 volts, 1.64112 milliamperes, 1.64112 milliamperes, that is what is going into this junction right here and what is coming out of that junction there. We can also find the current flowing across F using Kirchhoff's rules, because I can start here, I can work my way around. I'm going to gain 13.77 volts there. I'm going to lose it all, and since that's the only resistor we have here, I'm going to lose it all at that point. So my potential drop across here is 13.77 volts. Technically, if I'm going in that direction, it's negative. But using delta V equals IR, Ohm's law, I know that 13.77 volts is equal to the current times the resistance of F. And F is the sixth one right here, so A, B, C, D, E, and F. That is the resistance, so 9560. And so my current, and that's ohms, and now it becomes a pre-algebra problem. 13.77, 9560 divided by, and so I have, that's 10 to the negative third, so that's a milli, so 1.44038 milliamps. I am taking it out 5 decimal places because I rounded off earlier than that, taking it 2 decimal places because, well, we start out with 4 significant figures. We should be able to take it at least 4, but we still ended up with some strange rounding, so I do want to be overly cautious at this point. So my current across here, going in that direction, 1.4438 milliamperes. So now we'll employ another one of Kirchhoff's rules, the junction rule. So if we look at this point right here, the current flowing in equals the current flowing out. So the current flowing across E plus this current flowing across F should be equal to the current flowing into the power supply. So that's going in, comes out there. So this will be current of the power supply, 1.64112, minus what's going across F, 1.44038, and I get 0.2074 milliamperes. 0.2074 milliamperes. Well, now that I know the current going across E, I know what the potential difference is, because I know delta VE is equal to the current times the resistance of E. That's the current across E. I know what the current is. I'm trying to find the voltage, and so I just multiply that times the resistance, which is 46,800. And I have a drop here of negative 9.39484 volts. So again, let's now employ another Kirchhoff's rule. As I start here, I go across this, I gain 13.77 volts. I lose something going across D. I know I'm going to lose 9.3948 volts going across that, and then I should be back to 0. So this needs to be the difference between the two. And so what I find is that it works if my potential drop here is 4.37516 volts. Now I know the voltage across D. I can find the current, because the current is just voltage divided by resistance. And my resistance of D is 56,300. And so I have a current going across D of 0.07771 volts. And that is what's going into this junction. So I know coming down out of this junction is the 0.2074 milliamperes. What's going into the junction is this, and so this has to make up the difference because the current flowing in equals the current flowing out. And so I do the 0.20074. So the difference between those two is 0.12303 milliamperes. Now that I know the current going across C, I can find the voltage, because voltage is equal to I times R, and I know I. So times the resistance of C, which is 27,300. My potential difference, I lose 3.35861 volts. So now, let's do a Kirchhoff voltage loop rule. I gain 13.77 here. I'm going to lose going across either of them. Doesn't really matter which one I go across. I'm going to lose. I lose that much. I lose that much. And I should be back to zero again. And so I start out with 13.77. I lose that amount. I'm now going to lose 9.39484. And what I'm left with is my potential drop across either of them, because they're in parallel, is 1.01655 volts. And so I can now find the current going across each of them. So I take that number right there, and I divide by the resistance of A, 18210, and I have the current going this way is 0.05582 milliamperes. And what's going across this way right here is, I have that number divided by the resistance of B, which is 15,120, 0.06723 milliamperes. And now if I add them together, will I get this? And I get 0.12305. So already there's a rounding, even as far as I was taking it, there was still a rounding difference there. That is going to be considered close enough. Do recognize that if I had rounded earlier, then there'd be a huge discrepancy there, and that's one of the reasons why I took it out as many decimal places as I did. So that is the analysis, and so now it's a question of what do you get experimentally? This is the power supply that we'll be using. In theory, it goes up to 12 DC volts, but it really goes higher than that. 12 DC volts is somewhere around 100%, but we can crank the dial a little bit past 100%. The common code is that on the DC, there will be different colors. The red side is going to be the high potential side, and the black side is the low potential side. Over here on AC, that we have them as the same color. That's standard because the high side of the voltage and the low side of the voltage keep flipping back and forth, and so there's not a designated high side and low side. Now in the AC lab, for the sake of keeping things straight, I do indicate that we should consider one side high and one side low, but in theory it does flip back and forth. We have breakers here, so if you flip that, because occasionally I do hook something up wrong and it trips the switch, and there's one on the back also. Now, we have our meter right here. There are 3 ports down here. The port right here that says 10 amperes, nothing else next to it, the 10 amperes. This is used only if we are measuring something up to 10 amperes. Now, considering the resistors we're using, if we were running 10 amperes through it, they might start smoking, and it's bad for their health. I have burned a few resistors, and a couple students have burned resistors. It's just absolutely lovely smell when you start frying those things. So we are not going to do that. Also on the meter here, this is measured. It's a multimeter, so I can measure voltage. That's the symbol for resistance, so I can measure resistance, and we did that earlier. measure capacitance, measure frequency, and then I have for measuring current. So it's usually good to sort of calculate what you expect the current to be, so you know whether you'll be dealing with microamperes or milliamperes. And then you have the two ports. You have common, which is going to be the low potential side, and the other one, which is the high potential side. So I stuck with the color coding there for this, at least at this point. I'm going to take the high potential side of my meter and put it into the high potential side of my power supply. And then the low potential side of my meter into the low potential side of my power supply. And turn it on. Now we are above 100% on the dial there, so we should get more than 12 volts. And in fact, we do have more than 12 volts right there. Notice that it is positive. Now notice what would happen if I switch these. If I put the high side of my meter into the low side of the power supply, and then the low side of my meter into the high side of the power supply. First, just sort of speculate what's going to happen in terms of the meter. And, pause if you need to, because I'm about to show it. So what we have here is the negative shows up. We now have a negative voltage because you basically have switched it's like flipping an axis around. All right, but let's put it back because I want the positive value. But this does mean that if at some point I get a negative value, then that means I just have some wires switched around. So it's not a big deal when dealing with DC. It'll just make it positive. AC, does make a difference, the order in which you do it, because then you start getting into phase shifts, and that's another story. All right, so hooked in like that. Again, press in. Slightly different number than what we had before, so we just have to sort of settle upon something. Here's a sketch of what we are setting up, and here is the physical setup. So let's just take a moment to parallel the two. So we have the positive side of the power supply coming along, and then the current splits. At that point, the current can either go to A, B, D, or F. Over here, we have from the positive side, the current can get to this point and it splits. It can go to A, and notice that there's an A right below there. Goes to A, or it follows this path and goes to B, or goes this path and goes to D, or takes this path and goes to F. Well, that's F. Yeah, there we go, F. The stuff that goes from A and B connect up again and then come over here to C. C, D, and E all meet on the right-hand side. And if we come over here, C, D, and E all meet on the right-hand side. Current that goes from, so that's D right there, and then E is right here. E connects up with F on the F's lower side, which then connects up with the negative side of the power supply. So that is the schematic, and that's sort of the ugly truth of what it looks like. I have it set on 13. It's going to flip back and forth between several things there. Let's make sure I've got connections here. I'm looking at that right there. So we're going to set it at 13.83. Also, I want to point out over here, this is my spreadsheet with the numbers in it. And so down here, I'm going to put in 13.83, and it then automatically calculates all the rest of it. These numbers right here are the number of decimal places, so we'll just go ahead and make that big. This down here, the 4 sig figs, means at least 4 significant figures, but let's just go ahead and way overdo it. And that the ideal here comes from the color coding. And notice that the difference between the color coding and the actual value that we measured is 4.4% was the big farthest one that was off. We had a couple under 1%, so they could have put a gold band on there instead of just the silver band. Under 1%, so they could have put actually a brown band. Gold band would be plus or minus 5%, but we did better than that on almost all of them. So it's not that the cheaper resistors are worse than the more expensive ones, it's just that you can't guarantee. And that's places like DuPont, for you future chemical engineers out there, they place a premium on being able to hit specs as precisely as are needed. And so, the guarantee is what really makes things expensive. So for you who are older and you remember the 5.25-inch floppy disks, the double-sided ones have just been tested, but you can take any single-sided one of those disks in a hole punch and you can create a double-sided disk. And for those of you who don't know what I'm talking about, well, then you are younger than I am. So I'm now going to measure the voltage across each of the resistors. So I have the meter here across resistor A, and that is the voltage. So I should probably write some of this stuff down. I'm going to go with 1.016. I'm recording it here. I have this set up across resistor B now, and we have, it should be the same thing. Ideally, it's the same thing as what's across A, but you notice that there are some, it's fluctuating a bit. I'm going to call that there, 1.01. Seemed to be on 6. See if it flips back. I'm going to go with 1.017. So, there's a certain temptation to put down 1.016 just to have them match, but, try not to force the data. All right, so let's go to C now. So I'm going to take my leads here from the meter. And now just put both ends over here. The high end, the current's flowing from this way and then going down like that. So this is going to be the high end over here. Current flows from high electric potential to low electric potential. So if I do it this way, the way I just set it up, I should actually get a negative voltage. And this is just sort of to confirm, because I have the low side of my meter on the high side of the resistor, and in fact it is negative. I'm just going to ignore the minus sign, so it's 3.35 something, 355, 3.35. Oh, apparently it doesn't like what I was doing there. Seems to be settling down. I'm going to go with 3.357. For what I'm trying to get across here, it's not crucial to pin it down. Now across D. Isn't that so much nicer when it rounds off to 2 decimal places? All right, 4.38. So these are our experimental values, and then we will test it on that spreadsheet against the actual value. So that was D. So now we're going to set up on E. All right, so the high side is over here, because again, the current is flowing this way. And so we have I'm going to go with that, 9.4, dang it. and 9.42. And then F, all right, so it's now hooked up to F, and we should have basically what we had from the power supply. So it's 13.8 something. So 13.8. Let's just go with 3 volts. Let's bring it over and see how close we come to predictions. What we did on the paper earlier should correspond to what is calculated here. I inputted the voltages that we found experimentally and compared it against the ideal. If we notice that in terms of calculating the ideal voltages and currents, I used the actual measured value of the resistances. Even though that says ideal, that's, there's a huge error bar there. So I use these values here and the power supply here to be exact, and then everything else is based upon those. I guess so. Next step, so we did measured the voltages because that was relatively easy. Measuring the currents, complicated if you've gone through the simpler lab of it. So let's do the measured resistances and see how close we get. Now, when we're doing the equivalent resistances of the parts, we need to basically isolate that section. So let's set up. We're going to put this on measuring resistance. Let's first do AB. I want to isolate it. So I have AB isolated. I made the disconnect from there. And so to measure the equivalent resistance, I just need to connect here and then connect on the other side. And so now we get an equivalent resistance. And I should write this down. AB, we had 8260, because that's kilo ohms right there. So that's 8,260 ohms, which is what I wrote right there. And then we'll do ABC. Disconnect the meter. Meter disconnected, and then we still want to keep that separate. I've connected C into the circuit right here, and we find the total resistance by putting one connection on this side over here. I could have put it over there just as easily because they are connected by this wire, and then I take the other one and connect it to the other side of C. And so ABC, we have 35,590. I'm going to go with 590. And then we bring in ABCD. So I'm disconnecting that one right there. May as well keep this one in place because A is part of all of these that we'll be doing. Let's connect D into the circuit here. And D also connects on this side as well. So connecting D there. I've disconnected F and E from it. And so now if I want to find the equivalent resistance of A, B, C, D, again, one lead from the meter is here. The other lead needs to be on the other side of D. And so we have 21,810 or 20. Let's go with 810 ohms, 21,810. And now we're going to bring E into it. So let's disconnect that, reconnect E to it. Really don't want F as part of it, although it's incomplete circuit. It shouldn't make any difference there. All right, so I've connected the other lead to the other end of E. So A, B, C, D, E. We have 68,600. And now we bring in F. So really don't want the power supply. So let's just go ahead and disconnect the power supply. Matter of fact, what we can do, I'm going to take the probes out of the meter here, and just put them off to the side, connect up the circuit again, and is so much easier not looking through a camera lens. So I'm just going to disconnect from the power supply and put the lead straight into the meter. And so this should be the total equivalent resistance. So A, B, C, D, E, F. And why am I getting the exact same number? So let's, oh, because I hadn't connected F yet. There we go. So the whole thing, 8,380. Now we'll go to the spreadsheet and check it out. Based upon, I just entered in the measured values. This is what we had calculated it should be. And check out those really nice percent errors. Those are really good. All right, last thing is the current. So let's find out how close we come with the current. The next step is to measure the currents that are flowing out of or into each of the parts. Now, in terms of the setting here, this first one, setting up for milliamps, makes sense. These are all in amperes, so milliamps there. Microamps might make more sense for A and B and D. This one, milli or micro, I'm not quite sure which one's going to be better. Same with that one. And the last one, milliamps. So I'll be flipping back and forth between milliamps and microamps. So now let's go over here as we set up. I have it set on milliamps. The current flowing in should be the same as the current flowing out, so I'm not like in the other lab, the simpler version of Ohm's Law lab. I am going to pick whatever's more convenient. So right now I'm just going to do current flowing out of the power supply. So everything should be set up. We just went through the equivalent resistance and got values very close to what we expected. I have it set up here, just making sure current flowing out of that will flow into here and then into the circuit. We should get a negative value because of the way I have it set up, but we'll just ignore the negative sign. Since we're doing the power supply here, I'm going with milliamps, and let's turn it on. And so 1.63 milliamps. And it seems to be hanging out on 3 more than the other one. All right, so let's put this down, set up, turn that off. I want the current flowing into resistor A, and so I'm basically splicing it in after the junction. So this is the junction that was connected over here, but now it's going to split. Some of the current's going to go across B there, and then to D and then F, and the part that goes through A is going to have to go through there. So let's turn on some milli, and that just might be too small for that one. So what I'm going to do is I'm going to flip this down to micro, and we have 53.6 microamperes. And now let's turn this off and set it up for a current for B. I'm measuring the current that's coming out of B right here, so it's going to go, after the current goes into B, it's then going to hit this wire right here, go through the meter, and then connect up with the alligator clip I had that was connected right there. So turn it on, still in microamps, so 64.3 microamperes, 64 point, let's see which it seems to hang out on more. It seems to be like in 3, so we're going to go with that. Yeah. Turn the power supply off, pull the meter out, connect things up the way they were before. And now I want C. To measure the current going into C, basically this is what's coming from the AB parallel structure. I have it going through the meter before getting to C. And so let's turn this on. I'm sticking with microamps apparently. So that's 119.9 microamps. All right, so let's see which one it hangs out on more. Like watching the paint dry. Actually, it's because of where it's oscillating. I'm going to go with 120.0. Turn that off, reconnect, and now I want the current going into D or out of D, whichever one. So basically either put it between D and this combination or D and that combination. So I'll probably go for this one. I think it's a little more space over there. I set up the meter so that after the current goes through D, it's then going to go boom into the meter and then back into this junction right here. So, and that's coming from the meter right there into the junction. And so I'm feeling good about that. So let's turn that on. And so D, 76.3 microamperes. And again, I think I'm good with 76.3. Huh. I'm going to stick with 3. Turn that off. Pull the meter out, reconnect, and now for E. The current that is flowing out of C and out of D will join here to go flow over to E. And so that's where I'm hijacking the current. So I'm putting the meter right there. So the stuff that was going to E is now going to go through the meter and then back over there. So I'm feeling good about this current flowing into E. So I have 196 point, I'm going to go with 8 microamperes. Let's put it on milliamperes and just see what we happen to get. So we have the 0.9 there, and the other one was, or it might, yeah, 0.2. So it is actually between there what we had on microamps instead of milliamps, and so I'm feeling good with microamps. Let's turn this off. Take the meter out, reconnect, and then the current flowing out of F. The current flowing out of F would be, yeah. This was the point where the current would flow out of F, and so I hijack it at that point, forcing the current to go through the meter and then into the junction where it meets up with the current coming from E. And so that should be feeling good about that. So let's turn it on. And it is in milliamps. I talked about earlier that milliamps was a little bit better there. And I have 1.43 milliamps. Let's just see what happens if I put it on microamps. And I actually trust the milliamp more than I trust the microamp there. So there's more than a rounding difference there. So it really does matter what you're putting it on. And if it gets too big, then you really should be on the next higher level up. And so we're going to go with that. It's stuck with 1.43, even though it says 1.44 now. Hopefully it'll flip back, but there we go. All right, now I'm going to stop it there. So now let's go over to the spreadsheet. I put in the measured currents that we had just figured out. Let's move the cursor so you can see it better. And looking at the percent errors here. The biggest one is just under 5%. So apparently with those results there, the biggest percent error we have anywhere, well, there's nothing that we can do about that. That's manufacturing. But in terms of our predictions here, based upon the actual measured resistances and the power supply right there, it's pretty darn good. Because you know in physics, anything under 5%, you should be feeling good. Anything under 1%, you got bragging rights. There might be some credibility in the stuff that I'm trying to teach you.